prepare these assessment reports. Every 4 years there is a call, international call for governments. This is the not so good part. The governments just send the names of scientists who can be part
selected by the national governments.
And academic institutions is a difficult process, because at the very end the IPCC, this intergovernmental panel of climate change, this IPCC panel wants to get to the politicians, to get to the make decision people. So different governments have to be part, because otherwise you will be telling them what to do, but without taking on them. So.
And do the panels elect directors, or are they also assigned by governments?
I don't really know how the chair of each panel is nominated, is selected. I know there is a nomination at the governmental level, and then depending on countries, this goes down to scientific associations.
We're asking because of the scandals 2 years ago, all these issues that the director was overemphasizing things or using data incorrectly.
Yeah. There are this is a big problem. Is many things around, like bad use of data, bad science, this climate issue with reputed scientists in the UK that were supposed to do bad science, hiding data and so on.
Because he was an IPCC, right?
Yeah, he was part of.
Who in Spain is involved in the IPCC? No?
It changes for every period. Like this, in the previous report, 2007, only 3-4 people were included. I mean in the panels. Contributors, you have many more. And now this year, 9 to 10 people. But many people just don't want to be there. It's a difficult problem. But at least, if you look at the people doing this, they are reputed scientists. So there is some politics, but it was better in former times, because 20 years is a lot of time to start getting worse, but it is still one of the best examples of science organization in the world. Just to deliver a clear message to policymakers. So there is a clear signal, the signal is done that way, and there is no question about that. The vast majority of scientists are with this message, not with other messages.
Was the panel created with that name? So is climate change so old, the name?
Yes. Yes.
Climate change already.
So those reports are 1,000 pages reports, are difficult to read, but they also deliver a synthesis report, a very brief and direct message to policymakers. So it's 15 to 20 pages with more or less all the information gathered in a simple language. But the idea is that this is going to increase in Manuel. Like this. In the IPCC they collect information, they collect data and information which is done out of IPCC. IPCC is just a writing synthesis group. They don't make science. They collect science and make decisions on that. Okay? But they try to summarize all what is done and agree on a single message. So there is today there is a unequivocal agreement on the warming problem. So this is a signal which is present in all studies, all but a small number which are insufficient to make some fight. Okay? So there is a clear signal in the increase of global mean temperature. There is a a clear signal in the increase of sea level, and there is a clear signal in the decrease of snow cover. So you have confidence intervals which reflect the uncertainty as given by many different studies. So there are curves like this have been computed from many different sources, from 3 rings, from ice cores, from instrumental observations, from everything else. Anything that you can imagine that gives you the signal for a short or long period of any of those parameters.
And also, global mean temperature determined, is it the same as the land surface average temperature, or is it something different?
The global mean, you have thousands of stations.
So it's also it's a land surface average temperature. Is it the same? Or?
Yeah, it's okay. This is the figure from the last report of IPCC before this climate gate issue, and then there was a project independent from IPCC which is called the Berkeley Earth Surface Temperature, and they put here satellite information, also historical instrumental records, many different sources of information to obtain a very similar signal, in order to say that the signal of global warming was clear independently of this climate gate. So it basically is the temperature of the air close to the surface, average in the whole globe. And the thing is that they do look at the observations to look at the trends, to see whether we have the signal is strengthening or is weakening in the recent decades and so on. But they do also modeling, which is the interesting part for us. And modeling is all what you see, the temperature, the snow cover, etc., is a product of the climate system. The climate system, I talked about that in the previous seminar, so you know about that. But we have forcings, which are the solar radiation. This is the main one. Volcanoes, they put aerosols in the atmosphere, so they may obscure the atmosphere and make the radiation lower. And you also have this human contribution, which is in terms of greenhouse gases. So when we burn fossil fuels, we put CO2 and other gases in the atmosphere, and they have the opposite effect. They warm the atmosphere. The aerosols cool the atmosphere, and you have this almost constant forcing, almost constant in human scale time, not in geological scale. So they study all this idea, and what you have, this is the budget, the equilibrium of the incoming and the outgoing energy in the atmosphere. It's a complicated picture, but the idea is that you have the incoming solar radiation. This is short wave energy that partially is reflected by aerosols and partially is absorbed by surface. This absorption is later emitted, is heat that goes to the atmosphere, is long wave radiation, and this long wave radiation is trapped by the greenhouse gases. So a huge fraction goes down to the Earth. And then if you make the net incoming outgoing radiation, you have a positive small amount of energy that keeps into the atmosphere. So we have this temperature if this temperature keeps the balance. So the larger the
incoming and outgoing must be equal. So it only depends on the temperature of the.
It's not equal. It varies, and this is
in average. So I mean that's the equilibrium. The gap is at equilibrium the flux of energy. So it depends on how much greenhouse effect is that the temperature to irradiate what comes out has to be higher. Or
you have an oscillating net energy depending on the changes on all these factors. If all the factors were set to a fixed amount, you will reach an equilibrium with that average temperature in the Earth about this temperature.
In average.
In average, yeah.
So the geothermal energy source is not included there. Is it negligible? I mean, is it so small?
Which one?
The fact that we have essentially, we are burning fuel inside the Earth, so this heat also generated by the Earth itself, right? Well, just cooling actually.
You translate this geothermal, but this, you see so industries are burning things.
Yes.
No, I meant the natural thing. Geothermal stuff. I mean, the fact that in the core there is reaction going on and this generation of energy also.
Yeah, it's part of this surface radiation. Because you see this absorbed is 1/6, the emitted is much higher. So part is the heat of the proper heat of the Earth. But this is a complex thing that I'm not very I don't know very well all the details. So it's just a very introductory thing. So many of the questions that you may ask will be just flying in the air. I will not be able to answer. But the idea is, if you look at the so this is the aerosols at volcanoes, for instance, and the greenhouse is anthropogenic, is human origin. So if you look at the CO2, which is the greenhouse warming effect, this is the evolution of CO2, one of the, let's say, the main responsible of this effect. The evolution CO2 is blue, okay, and this is a scale of 400,000 years. So it's almost 500,000 years. Okay, so this is the geological scale. So CO2 has been going up and down, linked partially with glacial periods and so on. And the temperature of this temperature in red is very, very highly correlated. Not there is a delay, there is a lag, which is not always the same. So they go hand by hand, but in a non-deterministic way. So if you increase CO2, the temperature will be increased because of that, because of the previous. But it is not clear. Predicting the red in terms of the blue is clear to a first approximation, but not so clear. And you see, this is thousands of years.
How are they determined? Because you mentioned CO2 comes from ice cores, but the temperature?
Also. Because they look at the density of the air trapped in the ice core, and from the density they can estimate temperature. So this is very good science. It's one of the most, when you look at the details of how they compute from ice cores all the series, you get amazed. This is from the Antarctica. It's the longest. This is 3,000 meters. So, can you see that? Okay. So the idea is that this CO2 concentration have oscillated in this range, and the temperature have oscillated in a range of 10 degrees. This is more or less 10 degrees. But if you take this, the last 200 or the last 2,000 years here, if you take this very last piece of the series, what you would see is that we have suddenly increased the concentration of CO2 at a level which was never observed in the Earth. So we are much above the concentrations close to the double that are typically historically seen. And the idea is that we know for sure that the temperature will increase, but we don't know exactly when and how. See again? So because there is a delay here, so it's not.
It has already increased.
Yes, but not that much, not 10 degrees. So the equivalent for this increment of CO2 would be around, at geological scale, up to 8 degrees. But you don't even know whether the system will be stationary, will be stable. Maybe at some point the system will just break and make a transition to a different state that was never seen in the Earth. So this is a good thing for movie makers. So they have.
So how small is the sampling in the historical data? I mean, there could be very high peaks that you cannot resolve if they only occur for a short period or something.
Yeah, I can't tell you whether it is a year or.
Because from the average of.
But you have records going. You have records going not that far away from 3 rings, but going 3, 4, up to 5,000 years. They tell you a different thing. It's a sorted piece of the history. But yeah, there is a big consensus that this has not happened in the past. So I guess they are confident on the measurements, on the peaks, and so on and so forth. So actually, you have increments here, which tell you something about what is missing between one and another point. So then the idea is that if we look at the concentrations, this is what we have, and if we look at the temperature increment, it is much smaller. So this is the increment in the last 100 years, the last century, and the red is okay. This is a single year. There is a color bar here hiding below this panel. The red is about 1 degree. Okay, it's an increment in 1 degree in 100 years. So the effect of CO2 is still hiding there. So the problem is that this warming is not constant year by year. You have a spatial pattern. This is the anomaly. A particular year, 2005. This is the anomaly the following year, 2006. And whereas you can pick some regions here with a big warming, a particular year, they were colder at the following year. But in average, it's a global warming. Regionally, the details are not so easy to understand. So you need some model to see how things will evolve. This is the point of the modeling stuff. I already talked about that, so I will.
So the concentration of CO2 is it really essentially constant over the whole atmosphere, or is it say higher in the places where the CO2 is being generated? Does it diffuse very fast?
Yeah, very fast. Yeah. You see, for instance, when this nuclear power plant in Japan just exploded, to say, in less than 3 years, part of the emission were in the States.
3 days.
3 days. So it's very. You can assume that the concentration is homogeneous. In other words, that is the only thing that you can do, because you don't have measurements to give the model a spatial pattern of distributions, things like that. For aerosols, you do that. Aerosols are confined in different regions of the world, but CO2 atmospheric concentration it flows with the dynamics of the atmosphere, but it's not given as a spatial pattern.
Why not? Because there is no pattern, or because they don't measure that?
In principle, there is no pattern. There will be a pattern, but this pattern is you can think of that as a noise. Depending on the circulation, the CO2 can be slightly more here than there, but as a noise.
So the difference, this is not, the pattern is not for many aerosols, nitro, oxygen, many things. But now for CO2 is because the leveling that CO2, oxygen and nitrogen are principal component of the atmosphere. So the fluctuations, there will be regional differences, but the regional difference will be
much lower
than the
signal.
Average value. Yeah. So you just take the average value, which is the most important.
So you have models solving the equations. I told about this, and with the models you can just make simulations. Starting at a given, if you want to analyze the historical period, for instance, the last 30 years, where concentrations of CO2 have increased a lot, you can do that. You can initialize the model in a particular atmospheric condition, a particular day, for instance, 1st of January 1980, and then run the model day by day, hour by hour, until you get 30 years of data.
Which are variables? Is it temperature? So is it in the model? So can you back to
the basic, the dynamic variables are the position, let's say velocity, the three components.
The atmosphere. Okay. The velocity of what? Of the air of the atmosphere.
There. And the temperature, pressure, density, and humidity.
And the sea? You consider also the...
This model is for the atmosphere.
Only atmosphere?
Yeah, for the sea, for the oceans, you have a different model with salinity, temperature, and so on and so forth.
And for the global climate, do you not include that?
You include both. You include atmosphere, ocean, and there are some other models taking into account the carbon exchange, and you have also the soil. The water goes into the soil, and the soil evolves. So it's an important element also. And ice. So you have the cryosphere, the atmosphere, the hydrosphere, and the land. So the two components with longer modeling history are atmosphere, in the first, and then the ocean. The models for ice are very recent, and they are not as accurate as they should. And then you need to link all the models together.
And the biosphere also, so the activity of the biosphere?
Yes.
That's also included
in the land, yeah.
But
in the oceans.
And in the oceans. And this is the CO2 carbon sequestration.
Yeah.
So there are many elements that we know, and there are many elements that we know that we don't know. So there may be others that we don't even know that we don't know. But this is the evolution. So the uncertainty is huge, but if you take into account this huge amount of uncertainty, you still are able to model, to predict that the global warming will continue. This is why the climate community is so confident on the message. Because in spite of those big sources of uncertainty, the models are the signal is so strong that you could even do that with a much simple approach. Okay. So you have simulations, and those simulations are done at a particular resolution, typically hundreds of kilometers, and you have data availabilities usually 6 hours. Not hourly, but typically daily, but you also have databases with 6 hourly data. So for 30 years you have 15,000 maps, each map 100 points by more or less 10,000 points. And this is what you have to analyze in order to to do modeling, to analyze the results of the modeling, to do post-processing of the models. So there is a important thing which is internal variability. If you start the model in a particular initial condition, okay, you have the forcing. This is the source of predictability, the source of. But the model has internal variability, so it is a nonlinear model. If you start in a different initial condition, the model will do different things. Although at the end you will have a trend in the temperature because the trend is here. You are forcing that. So internal variability is an important issue which is neglected most of the times. And this is the simulation done by 3 runs. Each initial condition is a run. 1 to 3 runs of the same model for the same period. And this is the warming. So the temperature at the end of the period minus the temperature at the beginning of the period, to say. Okay. Then you can see that although you have a clear global warming, the regional signal is changing. Okay, so even with a single model, you have an uncertainty which is given by the internal variability, by the nonlinearity of the model itself. Okay? So this is taken into account when doing the assembly of simulations of products. And then what was the first result that was obtained by the IPCC, by the climate community, and that gave so much reputation to the panel? Was the attribution runs. In the attribution runs, you start the model in the 80s, in the 70s, and then you run the model with and without the anthropogenic signal and analyze the differences. So what you have here is all forcings. The red curve is observations. This is the curve that you saw at the first of the talk. And the black curve, there are several black curves, several models, or one model with several initial conditions. Okay. The black curve is a simulation, and this is the global warming, the mean average temperature with mean zero. Okay. So you can see what when you include all the forcings, the models do a pretty good job. But if you take out the anthropogenic forcing and you only consider the natural forcing, this is what you get. This is the black curve. So this increasing signal in the last 30, 40, 50, depending on the region where you look at that, warming is not seen in the models. If you put the anthropogenic forcing, this is the concentration of greenhouse gases in the atmosphere, the increasing concentration, and you take out the natural forcing, you don't consider volcanoes and so on, aerosols, big storms of dust in the Sahara desert and so on and so forth. You don't consider fires, all those are natural forcings, putting aerosols in the atmosphere. You still have this warming signal.
Just to understand, in the first panel you showed on the left-hand side.
This one?
Yes. It still has the increasing CO2 level as driving force?
No. What you have here is the effects of the aerosols. So volcanoes, fires, and so on. And the concentration is kept constant at the level of the pre-industrial scale. You start the model in the 70s, and CO2 is constant. You keep the same concentration as it was in the 70s. So you remove the anthropogenic signal. And then you do the simulation. Imagine that the industrial revolution don't take place in the Earth. So this could be the possible result. Now you put the industrial revolution in place, and you have this warming in the model. But this is what is called the attribution experiment. You take one of the factors out and you analyze whether it is causing the trend or not. So this is what helped the community to say what was evident anyway, which was that the CO2 warming effect was there, was the one causing this. And that was done with models. So that was the first time that something could be said at a scientific level about this warming. Okay, and then for the future, we have up to 2010, we know these concentrations, we can run the model up to 2010, but then here we stop, because we don't know the future concentrations. This is why they deliver scenarios. What is a scenario? Is a guess, a complete guess of what the society in the future could be like, and in that case, what the concentration of gases would be. If we keep relying on fuel fossils, then we will keep this increasing the concentration. If we go to renewable energies, to more green society, the concentration will be lower, and so on. So there is a big stuff which is economics and socioeconomics people working on that, thinking about how the future will be. But at the end they put curves. This could be the worst scenario in the future, this could be the best scenario in the future. And for sure the scenario in the future will be out of this, for sure. Will be, you don't know how the society is going to evolve in 30 years. It's completely unpredictable. But at least you have the projection of what could happen if you go this way or you go that way, independently on whether you go on that way or not. So if you keep burning fossils, you're going to face this situation. If you go to a green world, you will face that one. And you think about which world do you want for the near future.
What is in the vertical axis?
This is the forcing. This is the incoming energy, the net energy that comes into the ground.
CO2 concentrations.
Yeah, not CO2 concentration. You have a similar curve for CO2 concentrations, and CO2 concentrations are mapped in net energy coming to the surface of the Earth. Is the first arrow going down to the Earth?
Not because the sun is increasing, but because
not the sun.
The greenhouse effect.
Yeah.
Plants.
So the Earth keeps storing energy. The Earth is keeping.
So more or less, this is the net energy in the balance after this balance.
Exactly.
So you have the incoming energy, you have the greenhouse gases, and then you have this balance as larger the density, the concentration of the warming, as larger the net energy that keeps into the atmosphere, and so more or less this is the forcing, the real forcing at the very end.
If the thing will be zero, then the temperature will stay constant.
Yeah, zero is present situation. So we are increasing that in terms of these watts per square meter. So it's related to the first figure. So it's the effective forcing. And the thing is that you don't have aerosols there because you don't know which volcanoes are going to explode. This is even a more difficult problem. So you can do this average of elements.
In the previous picture you showed, that was not a big deal.
This is why they don't care. But this is what happened, not that is going to happen. So there is all this issue of economics, but at the very end you have this. This is the increment of forcing, to say. So you have the forcing for a historical run, and now you have the forcing. This is what we seen before, and now you have different scenarios for the future. I pick one of those scenarios and I run the model. Okay, I can run the model here, and I can look at the difference. Okay, the temperature at the end of the century as compared to the temperature in this historical period, as done by the same model. So this is the map of global warming. This is what appears in the news from time to time. Recently we had one of those maps in the news. There was a meeting at the ONU level of I don't know what, and they put a different picture in. Okay, and here you have warmings up to 8 degrees, depending on the scenario, depending on up to 8 degrees. And this is the thing. So
is there a reason why it's mostly in the northern hemisphere?
No.
Is it because of the mixing of the CO2? Or?
The warming is higher over land, so you have more land territory in the northern hemisphere. So this is why. But you don't know.
The sea is damping the trees.
Yeah.
Why is it higher over land? Is there any physical reason?
Yeah, because of the albedo, basically.
No, the warming, I mean,
because
there is clearly different, but
the warming over land, let's say the warming of the ocean is absorbed by the ocean, to say. The ocean, you have the proper dynamics of the ocean. We take the heat from the surface and balance the deep layers and so on. Whereas in the ground you have different processes going on.
Essentially, the heat capacity is much higher
Yeah.
in the sea. So
yeah, but
so
this is climate.
well, this 100 years, how long it takes to heat up the whole ocean? Probably that's a transient.
3,000 years.
Exactly. So that's a transient. So that's not a stationary point. So you keep warming it and you get an imbalance, so the ground is warming more.
This is related to the
This is the conveyor. So it should be larger.
Yeah.
The argument that you have more absorption, so that's more for the
Actually,
change.
actually thousands.
The
You heat
argument doesn't hold for the change. If the change is larger.
no, but in the ocean you heat just a very small layer, and the ocean is 3,000 meters in average deep, so it can absorb heat. Whereas in the surface, the heat stays at the surface.
So it's a transient process. So you are heating up and you are heating more north and the south. So that's how it absorbs more and more. And we are in a transient situation. It's not a stationary point. In 1,000 years, is nothing for the sea to heat up.
Yeah, there are reasons for that. It's quite reasonable. That I don't know the exact details, but you have different
Eventually,
physical conditions in the Earth and in the ocean.
in million years, probably we'll get everything possible.
Yeah.
100 years ago.
As the ocean warms, the CO2 level, the ocean captures CO2, but according to temperature. So, since the ocean has a delay with this temperature forcing of the sun, this balance is what at a short scale can be predicted, but at a long scale you don't know what is going to happen.
Is this enough to change the global circulation patterns or not?
Sorry?
Is this difference in the temperatures enough to change the global circulation patterns? Or
Not in principle, because otherwise the ocean models that are run do not contemplate this transient condition, this transient situation. Neither the atmospheric ones. So, in case that there is a change, a shift in the climate system, you will not see that with those models. But in case that there is a transient in the system, you are in the worst possible scenario that you can imagine. So, just it's worse than anything that you can simulate. So you don't need even to simulate. So But this is a hot topic now. Hot topic is tipping points. Obtaining conditions, obtaining thresholds above which there could be a sudden change in the whole system. This is a number of conferences are going on with that subject. Researchers started doing models taking into account all that. Looking at the ocean, because the atmosphere here doesn't play any role.
But if you're integrating the equations, in principle you could see the circulation, or you're putting the circulation as
No. Just forget about the atmosphere. The atmosphere has no problem. The problem is in the ocean. So the dynamics of the ocean are known to some point. So I'm not the expert on that, but I don't think you have a model to run simulations in the ocean for thousands of years. So the processes that you take into account, that you consider, are those that you know at a medium scale, not at a...
So the sea circulation patterns are put as a...
No, this is not true. But
No.
To change the parameters to obtain the present day, to get the right present day circulation, you put the Newton's law, but with some parameters in the viscosity around that, so as to effective viscosity, never to ones that match the present day currents.
in the values.
You don't know if the same parameters will be okay in
50, 100 years.
So in principle, you can do that. The small scales in the ocean are much more important than in the atmosphere. So doing a good resolution situation of the ocean is very difficult. It's much more difficult than the atmosphere. Of course, people do and predict changes in the Gulf Stream. People is doing that, but probably the amount of uncertainty is not that. I don't know if those improvements are included in the annual report. I don't know if they are included or not.
But since you run for a century, you don't run more than that. There are processes in the ocean which are not relevant at this stage.
They're not changing in 100 years.
It may happen that they may change, but you cannot model that because of the configuration that you did in the model. So the models are fit to observations, to reality. So they are biased somehow according to that.
But the energy balance will not be different. The Gulf Stream changes, this will have important effects on it.
Well,
But on Europe,
it will be a catastrophe. So
no, but Gulf Stream would be a catastrophe, but for Europe, not for the world.
I mean on a global scale, it's important energy
It may or it may not. I don't know. But for sure, for Europe, it will have a role. We will be like the States at the same latitude, colder, but for China, the conveyor is the big thing here, and the big dynamics of the currents, of the main currents in the ocean.
will not change in 100 years.
But I'm not familiar with that. That is not the main modeling stuff which is in the ocean models. It's mostly mixing But as you can see, it's quite complex, the whole thing. So what do we get out of that? Let's call them simple models, because at the very end they are complex, but they simulate what we know that is happening. So this is what we get. We use this is the problem of PDF. Imagine that you don't see this panel at the top. There are many lines here. Each of these lines is a global circulation model. So there are many modeling groups around the world, many but not that many, big institutions that have the experience for decades of developing modeling all those elements and running models. And those are the ones who contribute to this IPCC periodical report. What they do is they agree on different scenarios, present and future scenarios, and they all run the same forces in a way that at the end they can have some consensus information. They can probabilistically manage the uncertainties, the underlying uncertainties. So what you have is not a single model simulation, but dozens of that for different scenarios, for the future and for the present. And all that information is publicly available. So you can go there and get which variables, those that we already mentioned, and many others that are included in the parameterizations of the models, not in the dynamics, but in the fine-tuned statistical closure of the whole thing. So you have radiation, you have evapotranspiration, you have hundreds of variables at the surface, and you have also information in the vertical, and all that information is available there. So it's a huge, it's close to a petabyte of information. And this is temperature and this is precipitation. This is the bad thing of climate modeling, that there are many variables, but there are two of them which play a key role, and all the models are tuned to have those variables modeled properly. And the configuration of the models is quite biased anyhow. But this is the agreement. A point means an agreement. All the models give the same signal, positive or negative signal, more or less. And this is what you have with temperature. This is winter and this is summer. The difference of the last 21st century with regards to the last 20th century, 30 years each, 100 years of difference. So the global warming signal is quite coherent, and this is what you have for precipitation. And then in the case of precipitation, there are many studies using precipitation and considering one model, two models, one scenario, but depending on the region, if you, here for instance in Brazil, there is a negative, in average, there is a decrease in the total precipitation, but depending on the model that you pick, you can have it positive or negative. The average is positive, but the standard deviation is much larger than the average.
So
the signal means nothing.
The red means less.
The red means less precipitation. Then if you look at the Mediterranean, in the Mediterranean we have a partially coherent signal of going to a drier climate. But precipitation is not solved. You have some signals more or less clear, but the thing is global warming. Global warming is the consensus. Everything else is something that, even today, something that has to be analyzed in detail. So, let me see, because we are now. This is the problem with the models that this is the typical resolution of one of them. This is the French model, one of the French models. This is the typical resolution of the MPI model, the CAN5. So the problem is that the resolution of the models is, as I told you, hundreds of kilometers. So you don't have detailed information. So the model is not expected to reproduce the climate at a national level. It's intended to reproduce the climate at a global, continental level. So if you want to go from the global to the regional level, there are things that
in the previous figure, why do you have data just on land and not, why the colors on the land and not on the sea?
You have colors both in land and in the sea. This is just to make the point. For instance, for the model, Galicia is sea, it's not land for this model. So there is no Gulf, of course. There is no Estrecho de Gibraltar. The Mediterranean is a lake, it's not an ocean, things like that. For some models. So the resolution is poor for the pending mode. And then the idea is that in the last decade or so, there is a parallel effort for doing regional simulations. So it's another uncertainty ingredient. But what they do is, they consider different models with different. What they do is, if I have the future projections for the whole globe at a given resolution, I can just use a limited area model. So I will run the model not for the whole globe, for this particular region, and I will take the boundary conditions from the global simulations.
Is it the same models, just with a finer grade, or is it different kinds of models?
It's a different kind of model. Those models include dynamics which are parameterized in the global ones. For instance, the global models do not include vertical dynamics. They assume what, and in these models you have that. Most of them are non-hydrostatic. And they resolve things dynamically, whereas at a small scale, whereas the globals just do statistics with that. At a global scale, they don't care about cloud formation, about convection, about small things. So it's like a second generation of models, more complicated models. And then the idea is that you run that with boundary conditions and you obtain simulations for with a finer resolution, tens of kilometers, state of the art. So this is the temperature in Europe, this is the observation, this is the reality to say, and this is the simulation of a set, this is a particular regional model. So they don't do a bad job, in average. Okay. So at the end, there are many, at the end, now, if you are interested on data coming from those simulations, you have IPCC, you have the global simulations that I mentioned, but you also have now, from this Cordex experiment, this Cordex initiative is a voluntary, it's an unfunded initiative sponsored by WMO, the World Meteorological Organization, to coordinate the efforts in regional climate modeling in the world. It's like the IPCC, when they started coordinating the global community to do a comparable job, well, they are doing the same now with the regional modeling groups. So if you think of the Mediterranean Sea, you may not consider the global models, but the regional models in order to do some stuff, depending on what you are looking at. And there is a database where you can start downloading simulations. You have for this region, Europe, this is Eurocordex, MedCordex, Africa Cordex, and so on and so forth. And for this European and Mediterranean region, you have simulations already that you can analyze. For instance, there are a number of papers doing complex networks in the climate system. They take the points and try to connect those points which are correlated to say, even though they can be far away from each other because of this teleconnection issue of the atmosphere. The atmosphere, what happens here in the Pacific with El Niño affects the climate there. Okay, so you have some kind of a small world network like going on in the. So many people are doing that. But if you look at the papers, some of them are using the right data, but others are using the wrong data. They are taking data as the number of databases and models and is so big, it is difficult to have an idea of which simulation is the good one to do a work on complexity of whatever. And that was the point to give this talk. Okay. So if you if you have questions about that, you can ask me here or there when I go back, and I may give you some advice or even some data.
How transparent is the publication of the models that are being used?
It's very transparent. Yeah. There are special issues for instance, Journal of Climate for a particular model. For instance, NPI, when NPI develops the next generation, IFCA, for instance, they publish a couple of special volumes for the atmospheric model, for the oceanic model, with all the details, calibrations, and so on and so forth. And if you're interested in some data which is not stored in these central repositories, the modeling groups are willing to provide this data. As far as it is not very difficult to them to find it out in the archives. I mean, if you ask them for some particular variable, they may need to calculate something, and it may be difficult, but if they have the data, they will give you. So.
What about the models? I dropped the name of this institute in the US, which has been funded as an opposition to this one here. For example, to oppose the anthropologic effect. Do they have models as well that are available, and are they being tested by this consortium?
The idea, anyone can contribute to this. The name of the coordinated action is Global Model Intercomparison Project, and then they contribute to IPCC. So this is not an IPCC coordinated stuff. It's coordinated. It's called CMIP 3, 5, 6, 7. So you can contribute to that. They give you the forcings that you have to use, and then if you have a model that is published, you can publish some results with the model. You can deliver the simulations to them, and they will use them. They will compare with all others. They may discard your simulation if it is a clear outlier, but in principle it is open. This is why for AR5, so next year report will include over 100 models. Not tens, but 100.
I was referring to these arguments that solar activity might be an underestimated driving force. Right? Are there models which try to take that into consideration and try to simulate the changes based on that?
There are many papers in the last years about this issue, connecting solar activity with climate. And there were a paper in JGR, I guess, Journal of Geophysical Reports, giving some evidence of a possible influence between the solar, let's say, variability and the climate, but there is no consensus on that. So there are several papers published on that, and there is no clear evidence that in the short term the solar activity is playing a role in the climate system. It plays a role in particular things, but not in the global warming issue, for instance. So it plays a role in the for sure, in the way that they change the chemical reactions in the atmosphere. So of course they play a role, but not at the very end in the effect on the surface when you average over 30 years, 10 years. But this is also a hot topic of research.
Is there any data about the historical solar activity? I mean, because
yeah.
For example, by a sunspot observation.
Yes.
Yeah. I mean, of course, since you are observing I mean, probably they are measuring that since maybe 50 years or so.
More than 100.
There is a whole group of people doing scenarios. There is a scenario for solar radiation, and they combine all sources of information they have to have the proper signal of solar radiation in the past to force the models. So they don't force the model with a constant solar radiation. They put the proper variability, the proper events, that big storms, big proton storms and things like that.
But say the glaciations, are they somehow related to solar activity?
Yeah, of course, but they are not to solar activity, to our relative position regarding to that, the eccentricity of the Earth, and there are it's quite deterministic to some point, the 3, 4, 5 typical periods. So this is related with the Milankovitch. So. But this has nothing to do with this small line here, which is a century. What this is concerned with climate change. Okay, I think we need to start. Thank you. But just drop by and tell me anything talk about anything that I can. So now we can meet for half an hour or so.
Do you need to have lunch?
We have family lunch.
So let's sorry.
So if you hungry now?
No, I'm fine.
No, we can wait for half an hour.
Yeah, I can wait.
We can go up to.
José, habíamos hablado, a ver si iba a hablar contigo si te vais a los del proyecto
Sí.
Esta semana no vamos a volver. Tú estás todavía la semana que viene, ¿no?
Yo la semana que viene tengo que ir a Santander.
Estás todas
Sí, pero luego vuelvo. La semana siguiente es la de...
¿La semana siguiente es la del 2?
No, es la del... Esta es la del 25. Esta del 25
pues es
la última que voy a estar aquí.
Pues luego, pues a ver si entonces podemos juntarnos esta semana que viene.
Esta cuando queráis, o sea, me mandéis un correo tal día, tal hora, y ya está.
Así podemos.
Sí, consulta, sí, estaría bien. A ver si me da tiempo a ver alguno de los papers que ves.
Yo no veo sobre todo.
Si tiene...
I guess we come to
I d'on se sentia, aquí. Nosaltres estàvem sentats aquí, aquesta zona d'aquí.
Aquesta part coincideix amb això, dic,
clar,
clar,
i encara que no hi hagi l'aire condicionat no estava en marxa.
Mira, arxivant aquell que ha arribat,
clar,
això coincideix amb allò d'allà.
Clar, i per aquí entra, i esclar, està sentat aquí, o aquí dalt, que ha estat tot això aquí, i aquí això està igual. En canvi allà, se sent molt més. I el que surts de fora, jo obro la porta, que allà fora no estava a la cadena, i quan m'ho vaig d'aquesta finestra d'aquí, que esclar, suposo que tot el que venia aquí s'anava cap aquí, i un altre món. No, esclar, per el postim no s'ha... és que te'l juro, és que n'hi havia per vomitar, o sigui, és que era una... Vamos, era merda.
Això hauria de passar un dia que estigués aquí, la rectora fent tant...
Exactament,
El problema és que aquestes coses passen quan no hi ha
clar. I el millor segons com, doncs sí.
Científico tècnic, bon dia. Sí? Què tal, mana? És que estic aquí en el soterrani, mana. Bueno, doncs... I llavors, saps? Que ho diguem allà. No, doncs sí. No, que va, en absolut, del contrari, no? De fet, ells recolleixen les paqueteries més baixes. Jo ara, bueno, tu pots obrir-te, perquè tens clar, però bueno, jo ara, estava mirant un joc, no tens clar d'aquí, però jo ara,